Back in 1968, a mathematician named James Simons dropped a paper that would literally change how we understand the shape of the universe. It was an absolute masterpiece, and it basically revealed a hidden rulebook that governed space itself. So, what was this big secret all about?
Well, it all starts with a pretty simple question. Have you ever wondered why a soap bubble forms a perfect sphere? Or why planets take the most efficient path around the sun? It's almost like the universe is obsessed with minimalism, right? It's always trying to find the most economical, energy-saving way to do things. And believe it or not, that one idea is the key to unlocking this entire paper.
In math, this idea has a name, a minimal variety. The easiest way to wrap your head around it is to just picture a soap film stretched across one of those little wire loops. You see how the film pulls itself perfectly tight? It's minimizing its surface area at every single point. That state of perfect, tension-free balance, that's what it means to have a mean curvature of 0. It is nature's perfect shape. So to really get a feel for this whole minimalism thing, let's start by looking at some of the simplest, most perfect shapes that you can find out there in the wild. You know, the simplest version of this isn't even a surface. It's just a line. It's called a geodesic, and all that is the shortest, straightest possible path between 2 points. Now, on a flat piece of paper, that's just a straight line. Duh. But on something curved, like a globe, it's what we call a great circle. It's the one-dimensional version of that exact same universal law of minimalism. Okay, but that's all well and good in our familiar, flat world. What happens when we take these ideas and, well, we venture into stranger, more complex universes? See, we're used to living in what mathematicians call Euclidean space. It's a flat world where all the geometry you learned in high school just works. But the places mathematicians like to play in, they're called Riemannian Manifolds. And these are fundamentally curved spaces where the rules are totally different. Just think about the surface of a sphere. You can have 2 lines that start out perfectly parallel at the equator, but they are guaranteed to crash into each other at the poles. It's a whole different ballgame. And this right here, leads to the absolute crucial question. Does our simple soap film idea still work in a universe that is itself all bent out of shape? Or does the weird geometry of the space around it start to impose its own set of rules on what shapes can even exist? This was one of the great unsolved mysteries in geometry for a very long time. And this is where James Simons' 1968 paper just changes everything, because he didn't just solve the problem for one little specific case. He went and discovered a universal rulebook that applies absolutely everywhere. You can see his ambition right there in the opening lines of the paper. He basically says, look, I'm going to do 2 things here. First, I'm going to lay out a whole new general theory for minimal surfaces in any curved space. And second, I'm immediately going to use that new theory to solve some of the biggest open problems we have. Talk about calling your shot. At the very heart of his paper is something he called the fundamental equation. Now, you don't need to be a mathematician to get this. Just think of it like a law of nature, kind of like Newton's law of gravity, but for geometry. It's this one, single, elegant formula that describes how any minimal surface has to behave, no matter what kind of weird space it's living in. And what this law did was reveal a really deep connection. On one side of the equation, you have the surface's own bending, its intrinsic curvature, how much it twists and turns all by itself. And then, on the other side of the equation, you have the curvature of the space it's embedded in, the bending that's basically forced on it by the universe around it. Simons' equation was the missing link. It was the mathematical bridge that finally connected the geometry of an object to the geometry of its world. So that's some pretty heavy stuff. How did Simons even test this new universal rulebook of his? Well, he took it for a spin in one of the most classic mathematical laboratories there is, the perfect sphere. Okay, so what's the most minimal you can get on the surface of a sphere? It's something called a totally geodesic surface, and the equator is the perfect example. See, it has no extra wiggles or bumps of its own. All of its curve comes directly from the fact that it's stuck on the surface of a sphere. It's perfectly smooth. But what if you have a more complicated minimal surface living on that sphere? One that does have its own wiggles? Well, this is where Simons' equation showed there's a critical limit. Turns out a surface can only bend so much on its own before the background curvature of the sphere just makes it completely unstable. It's like a bridge that's trying to support way too much weight. Eventually, it just collapses. And he calculated that limit with absolute precision. This crazy-looking expression here is now famously known as the Simons threshold. Now, don't worry about the symbols. That's not what's important. What matters is the idea. This thing is like a universal speed limit for curvature. It tells you the exact tipping point where a minimal surface becomes so unstable, it just plain can't exist anymore. And that leads to this really powerful conclusion. If you ever find a minimal surface and its own internal curvature is below that threshold, well, it doesn't have a choice. It is mathematically forced to just snap into place and become one of those perfectly simple, totally geodesic shapes, like the equator. The universe's own rulebook puts a strict limit on what shapes are even possible. Now, hold on, because this is where the story takes an amazing turn. It turns out that this incredible discovery about curved spheres held the secret key to solving a completely different, decades-old problem. A problem that takes place in an infinite, perfectly flat universe. This was the famous Bernstein conjecture, and the idea sounds almost obvious. It just says that if you have a minimal surface, like an endless soap film, that stretches out to infinity in every direction, doesn't it just have to be a perfectly flat plane? I mean, it seems like common sense, but proving it was incredibly, fiendishly difficult. And for decades, mathematicians had just been chipping away at it. It was proven for 2 dimensions, way back in 1915. Then in the 60s, others knocked out dimensions 3, 4, and 5. Then Simons comes along with his new toolkit and proves it for dimensions 6 and 7. And then, and this is the wild part, just 1 year later, a different team proved it's completely false for dimension 8 and higher. Simons had pushed the problem right to its absolute breaking point. So how did he do it? How did he connect curved spheres to infinite flat planes? Well, it was a stroke of absolute genius. He realized that if you had a non-flat, infinite surface, it would create a special kind of mathematical object called a cone. He then used his stability threshold, that rule he discovered for spheres, to prove that in 7 dimensions or less, these cones were just fundamentally unstable. The only way for the cone to be stable was for it not to exist in the first place, which meant the infinite surface had to be perfectly flat. It was just a breathtaking connection between 2 completely different mathematical worlds. When you step back and look at it, the legacy of this one paper is just immense. It gave us a universal equation for geometry, it cracked a 50-year-old problem, and it uncovered these deep truths about the nature of spheres. And beyond that, it laid the foundational groundwork for so much of modern geometry and even theoretical physics. Fields like string theory rely on understanding the geometry of these strange, higher-dimensional spaces. It really makes you wonder, doesn't it? What other profound, universal truths about our reality are still out there, just waiting for us, hidden in the beautiful language of pure mathematics?